what we are going to do right now is we are going to derive the equation for the center of mass of a non-uniform rod. What the heck does that mean? Well, first of all, let's take a look at a uniform rod. A uniform rod, I need to explain to you what we mean by linear mass density. If I have a uniform rod, that means it is all made of the same stuff and it's the same density throughout. So let's say this has got a mass M and a length L. What we call the linear mass density, lambda, equals linear mass density. Now, normally density is measured in what units? Kilograms per, not density. If they say, what's the density of lead? You're not going to say, aha, kilograms per meters cubed. That is the density of any solid object. However, this is called linear mass density. It is the amount of mass per unit length. For a uniform rod, the linear mass density is just M over L. It'll be in, what will the units be? Kilograms per meter. This is just the number of kilograms per meter that this rod has in it all along its length. This is a uniform rod. This is easy to find the center of mass of. Where is the center of mass of this? At the center. Boom. Right there is the XCM. Okay? It's much harder to figure out the linear mass density of a non-uniform rod. Here is a non-uniform rod, and I'm going to show you what that looks like by doing something like this. The idea here is that the density somehow changes. So in other words, like it's low density here, and the density starts to increase, and such that when it gets down here, it's like super dense. Let's say lambda, the linear mass density, they'll still be in kilograms per meter, but it could be something like, for example, let's try if the linear mass density is some constant times x. Let's make it Cx. And that constant, you can make it 3, you can make it 10, you can make it 14. This is just an example if you have a some constant times x. So if you go twice as far along this the length of this rod, so in other words, here's one density right here. If I go twice as far, how much more dense will it be? Twice as dense. This is a relatively simple relationship right here. How are we going to figure out the center of mass? What I want to remind you first is, if you have discrete particles, meaning particles that are just separate, XCM is equal to the sum over all I of MI XI over MI. Now, what the heck does that mean? You guys realize that if I is just a counter for I equals 2, something like that, this would be M1 X1 plus M2 X2 over M1 plus M2. That's all that means. This is just one example with I being 2. Okay, now what we want to do, and this is something we can do forever, is we're going to take this and we're going to see what would happen if instead of two discrete masses, M1 and M2, I had an infinite number of different masses. All of mass, what are we going to call the mass of some arbitrary section of this? And I'll color it in with red. What are we going to call this? And that is, I'm showing it too wide. I need to show it infinitesimally small. But what do you want to call that little teeny weeny, insy bitsy, infinitesimal piece of mass? dm. I'm going to label that dm. And while we're at it, if we're going to call the right and left direction the x direction, what is the width? From here to there, what is this teeny weeny, insy bincy width of that infinitesimal mass element dm? dx makes perfect sense. Now, so now let's go ahead and see how the heck we're going to find the center of mass of this non-uniform rod. So if we're adding up an infinite number of things instead of like 3, 4, 5 or something like that, what does this summation turn into? integral sign. So let's go back to this color. We want to do this integral. So xcm will be the integral. Instead of one of the masses, what am I going to put instead of like mass 1 or mass 2? There's got to be an infinite number of them, and they got to be all infinitely small. What am I going to put instead of mass? dm, right? That infinitesimal tiny mass, dm. Okay? And then instead of x, well, we are going to just put x. In general, you could put r, but we're in the x direction, so that'll be x. And then I got to divide it by what? So the integral of what? What is this? When I add up all the mi's, what am I getting at the end? Total mass. How am I going to write that in integral notation? The integral of, all you're doing is you're adding up all the dm's, right? All those infinite number of infinitesimal dm's. It's just this. We just have to integrate dm. Basically, instead of mixi, it's dm times x. And how many different x's are there? There's an infinite number of them. Okay, so now here is the challenge that we have every single time that will continue in second semester. We got to express this dm in terms of space variables. Notice I've got x dm. I cannot integrate that yet. I need to get, if I'm going to integrate x, this has got to be what here? Dx. I got to somehow turn it into something with dx. Now check this out. Do you understand, or does this make sense, that the dm, well, let's look at the uniform rod case. If I wanted to find the mass, what would I multiply lambda by? If I wanted to find the mass m, what would I multiply lambda by? The length. Now let's take that on an infinitesimal scale. We're going to, right over here, dm is going to be equal to what? Lambda times what? Now here we can't use the whole length because this is just a little tiny dm. dx. Cool, now we got it. So I need to express dm as lambda dx. It'll be the same thing when we do charges, but it'll be lambda times dq. So I'm just going to rewrite this, and this is the integral over the entire length. The entire length, I'm just going to write that right there. We'll put in what that actually means in terms of our limits in a minute here. It's over the entire length of this. All I got to do is add up all the x's and their little dm's that are there, and then divide by this is just the m total. So I'm going to rewrite it like so. This is the integral of x times lambda dx. And this is the same thing, integral. And if you want, for integral dm, you can just write m total. I'm going to keep it integral dm because we're going to have to integrate that as well. Okay, so this is how we get there. And now I can rewrite this again. What actually is lambda for this situation? Let's look up back there. It's some constant times x. So I'm going to rewrite that. Lambda is just cx, that's lambda right there, times, and then that's this whole thing together is dm. And then we go like this, it's over the integral of, and let's go ahead and plug this in. dm is, I can express dm as lambda dx, which would be, let's go ahead and do this, cx dx. Now you may be tempted to say, oh, I'll just cancel. You can't cancel yet, because we have to integrate first, as it will turn out, c will cancel. So that will cancel, but we have to integrate first before we can do any cancellation. What do you get when what is x times cx? Or what do we get? Cx squared. When you integrate cx squared, let's go ahead and do that. I'll write it out so people watching on the video can check this out. It's cx squared dx over integral of cx dx. When we integrate that, and let's go ahead and do that, I'm going to actually add the limits in now. What do we want x to start at, and what do we want x to end at? And the one thing I forgot to do is put this on here. The length is still going to be L. Where do we want to start adding up our dm's? At what x value? I'll give you a hint. You can pick any place to be 0 that you want. I'm going to pick this to be 0 because it makes the integration very easy. We want to integrate from what limits of x? Where's x going to start? 0, where's x going to end? L. So those are the limits of my integration. We're going to integrate from 0. I like to put what variable. Does x equals 0 to x equals L? Same thing, just 0 to L. How about for the total mass? Do we have to integrate from 0 to L as well? Thumb up if yes, thumb down if no. Do we have to integrate from 0 to L for the total mass? Go ahead and vote on that so I don't have to call on you. Yeah, we do. We got it. We don't want to leave out any of the mass. We're going to integrate from 0 to L. 0 to L. Now, let's go ahead and integrate. What do you get when you integrate cx squared, or find the antiderivative if you guys are still talking about those? What do you get? Cx cubed over 3. So this will be cx cubed over 3, but then we have to evaluate that. And this is the notation that we use. You evaluate it at the final point, and then you evaluate at the initial point, you subtract that. This one will be, wait a second, it's not same thing. What is this one going to be? Aha, so we got cx squared over 2, and we're again going to evaluate that from 0 to L. When you evaluate that, all that means is you plug in L, and this is, let me put this line here so we can keep that separate. Okay. You plug in L, that'll just give us CL cubed over 3, minus, you plug in 0, what do you get? You're going to get 0. So cool, that's going to be easy. Same thing over here. We're going to get CL squared over 2, and then minus 0. So now we get down to brass tacks here. What does cancel that we can see? Doesn't matter what C is. Cool. So now, just to simplify this, I've got L cubed over 3 divided by, over 3, all divided by L squared over 2. What does that give us here? Okay, so I think you're right there. This is like multiplying by 2 over L squared. We get 2/3 of L. Guess what, folks? That is the center of mass of this thing. It's that easy. 2/3 of L. Notice what's cool about this. What canceled and doesn't even matter? The constant C. So in other words, if the linear mass density is 2x, or if the linear mass density is 3x, or if the linear mass density is any number times x, you still get 2/3 of L.